Okay, so homework is due today, though I think most people have turned it in already or they're using late days. The next homework is also posted. Put it up this morning, and it will be due 2 weeks from today. So that will cover through the end of power flow and a little bit on power electronics, which we'll finally get to today. So the schedule for today will be, it's actually going to be our last unit on power systems, and then we'll move on to control after this. So what we're going to talk about first is power markets. We're going to finish that up from last time. There's only a couple slides left. We'll talk about how power markets differ a little bit from traditional markets and sort of how we compute those differences using optimal power flow. And then I'll finally talk about this little I've been trying to get through for a while on power electronics. I keep lying, I guess, because I keep saying I'll post this as an online lecture, and you'll see why this was actually kind of hard to do. The various hardware I'm showing here doesn't work with my video creation software, and doesn't work with the Mac. So bringing in a whole big setup, hopefully it'll all work. You can see some interesting demos. So this is really worth it. It's kind of cool to actually see these things, see what power really looks like for real devices. So it's kind of cool, but well, hopefully it's actually worth all the headache it's been thus far. So first of all, were there any questions about the homework itself? Or I guess the homework is over, so you don't probably want to ask questions about that. But are there any questions about what we started to cover at the end of last time with power markets? And if not, I'll just jump right in. So what we were talking about last time was this idea of how a power market works. And it has to work like this because there has to be a way that you actually can have a centralized entity that's in charge of making sure power is generated when it's needed to. And this is really more for kind of the large scale, keeping up with sort of the large amount of demand people have, not kind of the margins. Because when you do return, I mean, we can forecast how much load people are going to consume as a whole, right? That's what we sort of saw in those first few classes. But there are obviously little variants. It's going to be almost impossible to ever get perfectly right, because I could choose, in some sense, right, to turn on a light or not, and that will change a little bit the demand. So the little bits in the margins are actually made up with using a different system than this. This is really the market for kind of the big allocations of power that you want to do at the grid level. So the way that works is that the loads all report how much they're going to need. Again, it can be approximate, but they report how much they're going to need to this central operator called an ISO or an RTO or something like this. And then the generators independently also give their cost functions, or some surrogate for their cost functions. Hopefully it's their true cost, but maybe it's something like a cost which they think they're going to make enough money on. The ISO is the one that solves power flow, and this sort of takes it out of the hands of the generators themselves, because unless they're all managed by the same person, it's hard for them to kind of agree on anything, or it would be hard for them to kind of agree on anything while keeping things secret from each other, I guess. And so then the ISO is the one that kind of is trusted with all that information. They then solve optimal power flow, send the generation back to the generators, and then when the time comes, the generators have to generate their desired amount. And they pay a penalty, a pretty big one, if they don't set it, if they aren't unable to meet that demand. And then finally, of course, they'll turn on their desired amounts, and then power flow, just physics handles the rest, right? Physics kind of determines then that this will in fact be how power actually flows to the network to reach all the loads. So that's kind of how it works from a high-level standpoint. But I'm going to go a little bit more in depth in it now and talk about what is the actual optimal power flow problem that you need to solve for a market, or what's one they typically solve in a market. And to do this, we're actually going to be a little bit more, and we'll talk about both the problem itself, as well as how you compute things like the equivalent notion for these marginal prices, which I talked about in sort of the economic sense. The marginal price is the cost at your current generation amount of a little bit more of a good, I guess. So I talked about that for kind of a general firm, but we'll talk about what the analog is in power markets. To do this, though, I'm going to be a little bit more general than we were before and assume that every node has a generator and a load. It's just easier that way. Some of these can be constrained to be 0, but let's just sort of, while we're there, just so we can have talk about P of P superscript G, for example, being the generation at each node. And that can be 0 sometimes, and similarly PL, or I guess I'm using SL. Basically, we're going to split the power at each node into a generation and then a load. And we're going to assume that they all have each of these. So, if the load, there's no actual load at one node, that would just be 0. If there's no generation at one node, that would be 0. But it's just easier if you think about splitting these things up explicitly for each point. Because what we are going to control, what we actually have control over as the sort of scheduler of power is we assume we can't really control the load, right? So we only control sort of some portion of the power at each node. We control the generation at each node. And so it's important to kind of think of what we control, what we can control as a system operator versus what we cannot control. So as I said, we'll take the SI, which is the power injection at node I, and just separate that into these two components. These two, importantly, are both positive quantities because our convention was that a load was a negative power injection. But we're subtracting off SL here. So SG and SL are both, but they have to be positive quantities in this definition here. And now let's look at what an example of a power flow, an optimal power flow problem would be for a power market. What would the actual ISO want to go and compute given all its cost it's gotten, given the demands, etc. And this is a pretty general formulation. There are probably a lot of other things you might want to constrain as well. But this gives a reasonable idea, actually, about the kinds of things that you might want to constrain or optimize in an optimal power flow problem if you are a market maker or an ISO. And so I'll just go through each of these terms in each of these little terms optimization problem one at a time. So the first thing is that we want to minimize over z. Remember, z still is this vector. Actually, no. That's a typo there. It actually should be this. It should be minimized because you don't really minimize over the, you wouldn't minimize over the L. So I guess now z, before z was equal to all these things, was equal to theta, v hat, p, and q. So z is how I defined this before. You optimize with that, but really this is the generation here because you assume the load is fixed. So you actually assume that you're just optimizing the generation. Now, you do optimize over things like Q as well, but those are the ones that are going to be defined by the problem statement itself. So these ones will actually be fixed by the loads. So I'm using this as a shorthand to say we're optimizing over all these things. Some of them are variables. Some of them are actually fixed by the problem statement. But you can always include them as variables and then add a constraint to that variable saying it's equal to something. So it can oftentimes be easier just to optimize over the entire set of variables rather than make a complicated set of what your actual optimization variables are. Does that make sense to everyone, actually? Basically, I'm just saying that if you want to optimize over this, it's possible to say, I want to minimize over some function of z subject to q equals q naught, for example. I can write it like that. And it can often be a little bit easier than trying to determine in this formulation what the different variables are that we know and we don't know. So being a little bit informal here, but the more important thing is actually to sort of see what these different constraints are. So we minimize over z, which is a collection of all our variables that we care about. The cost of p superscript g. So P superscript G is the real power component of generation. And this is the most common objective for optimal power flow and power markets. Because what costs money is generating real power. That's sort of the, how much gas do I need to burn to make my turbine actually spin. That corresponds to real power. And so what we're going to do is we're going to minimize the cost of all our generation. And this cost, which I write as this one function c p of g, this naturally decomposes into the sum from I equals 1 to n of the cost of generation at node I. Sorry, ci. So what this is saying is each different generator has its own cost. And the total objective is just the sum of all those costs because that's how much we have to spend to generate that much power. Now, there are, of course, going to be, I'm summing from I equals 1 to n here, where n is the number of buses in the network, so it's the number of nodes that we have in our network. And as I said before, some of these nodes will not have generators on them. And so the cost, you can choose whatever you want for the cost there, because there'll be another constraint elsewhere that the generator, say, at node 1, if there's no generator there, has to output 0 power. So yeah, another constraint like that. But you can just assume that there is some cost, even if it's irrelevant, at every node. So that's the first term. We want to minimize the cost of generation, which is, again, you could optimize other things. You could optimize things like the carbon emissions of generation, stuff like this. But we won't worry about that right now. We'll just talk about minimizing the cost of generation because most markets don't worry about that currently. Yeah?
So it should be minimizing PGI instead of Z.
No, because here's the tricky part. Z is just sort of a variable of everything that we care about, but even though some of these things we can't really control, in this formulation, they still are variables in the optimization problem. It's just they're variables that are constrained. So for example, take the voltages. Those do not play into the objective at all. But if you don't allow those to be variables, if you fix them, then there may not be any power flow solution, period. So really you are optimizing over the things like the voltage as well. It's just that those are terms that don't factor into the optimization objective itself. They're just other terms. It's actually very much like in the L1 loss function, your objective was 1 transpose nu, right? But you were still optimizing over nu and theta, because theta was an element of this problem. It was, in fact, the most important element. It just wasn't in your actual objective, because it was determined by the constraints rather than by the objective itself. So other things in Z, and I was a little bit fuzzy about what Z was here, because it really isn't quite everything. You know, there's maybe it isn't. You know, it's just the generator power, not the total real power. But you still have to include other terms in the optimization problem itself, because they are variables that have to be defined by, or have to be satisfied. They are variables that you use to satisfy the other constraints in your formulation, essentially. So you minimize the cost of generation. So the next one's just power flow. SG minus S superscript L. Those together are just S. That's the total power rejection in each node. That equals diag V Y bar V bar. That's just our familiar power flow equation that has to be satisfied by these problems. The next one is an example of a line constraint. So this one here, I won't dwell on this first one because that's just power flow. This one here is a little more interesting. What this is saying is that this term here, so y subscript ij times v bar I minus v bar j, that is the current that flows from node I to node j, right? That's just the definition of current there. It's actually the conjugate of the current, but that's fine. It's the conjugate of the current that flows from node I to node j. Because remember, current's a complex quantity, and we take the conjugate because it's just we're going to work with power in a second. So we take this whole quantity here, we multiply it by v, and that then is the power, effectively the power that flows across that line. And actually, I probably shouldn't say that this is negative here. I should probably just put an absolute value around that. But I'm doing it for all I and all j. So this is actually goes both directions, essentially. But what this says is that a certain, no more than a certain amount of power can flow over any given line, basically. Lines have, I mean, you can think of it in terms of current, too, if you wanted to. Just there could be current ratings in the lines. But you can also think of it in terms of power ratings. It's a little more common to think of it in terms of power flow and power ratings, just because that's sort of we're talking about power flow here. And all that says is that this line just can't handle more than a certain amount of power flowing across it, from the current, really. Otherwise, it may melt or something like this that you don't want. And so we're just going to constrain that to be less than some quantity here, some maximum flow over line ij, where S, big capital S there is just a constant. It's just specifying the maximum power flow from across the transmission line between nodes I and j. And then you also have things like this. S superscript g has to be less than S superscript g max, where this is another just constant here. And that's a generation constraint. That is saying that I can't generate more than a certain amount of power at each generator, right? Generators typically have a maximum capacity they can generate. They can't easily generate more than that. Sometimes that's 0 if there's no generator at the node. But even for nodes with a generator, they will often have an absolute limit. There might be lower limits too, by the way. Things like nuclear plants are very hard to shut off, right? So you might actually have a lower limit saying this generator can't generate any less than something else, than some fixed amount. But you have all these limits, you have all these constraints in the generation, you have constraints in the lines, and so more than any specific kind of this is, optimal power flow for markets, the point here is just to kind of give examples of the type of constraints you will see in these things and you will want to encode in these type of problems. And the last point I want to make, and to start with the last point I want to make is, you can think of this whole process as essentially some black box function, right? Where the real input to this function, the thing that you really can't control here, that is truly external, is the loads on your system, right? Those are things that you do not have control over. You can control the voltages a little bit by turning the generators, essentially putting more current through those exciter magnets in the generators. You can certainly control the power to a certain extent. That's the real power they generate. You control the reactive power kind of indirectly. But the loads of the system are really beyond your control, at least in this thing. We're not assuming we have demand response or anything like that. It's really, there's loads in the system, and we do not control those. So you can think of this whole thing then as a great big function that is solving the optimization problem itself, as a great big function that takes in as input loads and determines sort of all the variables you get here, right? All the different settings for generation, power generation, for the voltages, for the reactive power, real and reactive powers, the voltages being having both real and imaginary parts. And so what pops out from this is both an optimal assignment to all the variables as well as the cost at that optimal assignment. Okay, so that's just thinking of it kind of one step above. In this problem, the inputs are a lot of things, but from a high level, what's the real input to the system is just what's the load going to be at the different nodes. And then solving this problem will output what's the cost of that, the best cost of that, and then what's the variables that kind of realize that best cost. And this leads us to the notion of what's called a locational marginal price. So in sort of the standard economics, remember I drew that, well, I actually had it a few slides ago. I had this figure a few slides ago showing that for a simple firm, the typical thing you do is there's some market price, you generate stuff up to the market price, up to the point in which the marginal price, that is the price to make one more good, equals the market price. This looks a little bit different, and this is sort of traditional economics here. This looks different in a very interesting way in power markets. Because what happens in power markets is that this marginal price can be different at different places in the network. Right? And sort of what this formally is, the marginal price here, formally is should I write it here? Yeah, it's the cost of generating a little bit more, in this case a little bit more power, but it's doing it at node I. And the reason why this can be interesting is because unlike in a typical environment where supposedly the cost to generate one more unit would be the same kind of everywhere, there's just one single market. Here it can actually vary at different nodes. So suppose that node I went from a load of 10 megawatts to 10.1 megawatts. The amount of total cost it would require the system to make up for that could be different from the amount of total cost it would take if that same increase happened elsewhere. And it's actually kind of intuitive why this could happen. I mean, in general, it can be intuitive why this happens, right? Because essentially, the cost of generation is different in different places. So just think of in terms of, there's a generator in node 1, a different generator in node 2. They have different costs, so of course there might be different costs to increase that. But interestingly, it also depends. I mean, that wouldn't be a problem if you could just take the power from any generator, right? So basically, if this generator over here costs some amount, and this generator over here costs a different amount, then obviously, increasing the load here versus the load here could differ because of these guys. But it wouldn't make a difference actually if you could just get whatever power was being generated over here instantaneously and freely over here, then you would just buy from this guy over here instead of this guy. The problem is that you might sometimes have to buy from a different generator, from this guy, for example, because this line could be congested. This one could be have reached its maximum capacity. And so all these effects kind of come into account here to make the price of electricity different at different locations in this network. And these are called locational marginal prices, or LMPs. And what an LMP is formally is it's the partial derivative of this C of Z star. So remember, we looked at power flow as being an input from a bunch of loads to a cost. Also that's variables, but just think of it now in terms of a single output function that takes as input loads and outputs a cost. What the LMPs are formally is they are the partial derivative with respect to that total cost. So how much does the total cost of the system change if I am to increase the load at node I a little bit? And that's formally defined as the derivative of this cost evaluated at Z star. That is the output of power flow. So it's not just, this is not equal to the derivative, for example, of the cost, the CI cost. It's the derivative of the total cost. So it's the total cost of the entire system when you solve power flow. If I am to change the load at node I a little bit. And so to compute these, you can compute them in one of two ways. One thing you can do, which is very easy, is if you have an optimal power flow solver, you just increment your ith load by a little bit, by delta, say, look at the difference in the resulting cost you get, and then divide by delta to kind of take a numerical derivative here. That's the kind of easy way to do it. In reality, no one actually does that because it would take a lot of computation to do it. And actually, when you solve these optimization problems, it turns out that these derivatives can be found very quickly using what are called dual variables. So when you solve an optimization problem, it actually gives you solutions for variables as well as some things, other things called dual variables that essentially act to enforce the constraints of the problem. And it turns out that you can actually get these derivatives very easily by looking at the dual variables. We're not going to do it that way in this class. Duality and optimization is a very important topic, but it's not one that we've been talking about in this course, so we're not going to do that. But it's worth knowing at least that this is the actual formula for an LMP. You can think about how to compute these numerically, and you will on the next homework. But in practice, they're not really computed in that inefficient a manner. So here's a simple example. I think this is my last example, though I have a few more final comments on power markets here. And really, it's more just so you have this example. I mean, you can go back through it again in the slides if you want. But again, I'm writing here what is known in the system. So what is known in the system, and though I guess actually I would also assume that some of these nodes you also know the reactive power. Sorry, actually, you should also know some reactive power loads at each node. But what typically is seen as the input to a system is the real powers. Reactive power is handled very differently from power than real power here. It could theoretically be handled very similarly with the market and all that kind of stuff, but the problem with reactive power is that the loss of reactive power over lines is very high. And so there's no point in generating reactive power a long ways away. You just lose it all. And so you have to handle it with little different mechanisms. So the markets people talk about typically are really markets for real power transmission, not for reactive power. So what's sort of given as input then to the system are the loads of all these different nodes. And the other input to the system is the cost of generation at each of these two things. And I'm not writing it here because now I'm actually hiding the fact there's a generator there because there's no generator. I mean, I could draw it and make the cost infinite or something like that, but I won't bother with that. The cost at these two generators are these things. And this is sort of a similar scenario that I gave before. I think this one has a higher linear term but a lower square term. This one has a higher square term but a lower linear term. So this is better at first, and then that one's better afterwards. So what you get if you run power flow, and let me sort of clarify what I mean by say when I run optimal power flow here. What I mean is I solve this problem using that repeated linearization technique that I mentioned in the previous slide. So this problem is approximately convex. These are a little bit nastier here, actually, but a simplification here is convex. And the one you work with in the homework is completely convex, except for that power flow constraint. So we take the Jacobian, we linearize around the current iterate, we solve that, and we repeat this process. And what we get out at the end is a list of allocations of power, which are given here. So the end result is we generate this much power at that node, this much power at that node. And then if we run the system again, varying the prices a little bit, or sorry, varying the demand a little bit at each node, you can see how the total cost will change with varying the different loads. And that's how you get the resulting LMPs at each node. So this is kind of what comes out of power flow. What comes out of power flow is an allocation of power as well as the LMPs for each node. And that's what you'll actually solve for the power flow, the optimal power flow problem in the upcoming homework. So looking at this example again, it's kind of intuitive, right? Because the LMP is the highest here at the node without a generator. That makes sense. Because it can't generate things locally, so when you generate elsewhere, you suffer some loss in transmission, and so it naturally costs you a little bit more to use power here, right? Because you're using both the power that you're actually consuming as well as the losses, you're implicitly using the losses that it took to transmit you that power. It turns out there can be a lot of so that one there is a very intuitive effect. There can be actually much more unintuitive behaviors here, including things like LMPs that are actually negative sometimes. So at some nodes in the network, it actually can be the case that at least in terms of the market, you will be paid to consume energy. And the intuition here, it's a little bit bizarre. The intuition here is that essentially the power flow equations and the transmission constraints, the fact that you can't transmit more than one power over a line, these can actually kind of conspire in weird ways to essentially make it that if you want to consume more power at a given node, you have to actually produce less power in one generator and more power in another, maybe cheaper generator. And so it actually will be cheaper ultimately for everyone if you consume power at this node because of these transmission constraints. So they can happen in very sort of weird, non-intuitive ways. I have an update to Adobe Acrobat. I don't want to install that right now. Did it actually? Okay, there we go. So it can be very unintuitive, and these are the idiosyncrasies of power markets that you would never get in a normal market, right? Or someone would pay you to buy their stuff. I guess unless there's a promotion or something like that, but I don't get into economics like that. So really here, what I want to emphasize here is that we won't go into the details. There are classes you can take on that describe these in much more detail here. But the nature of power markets are fundamentally different than a normal market. And they have weird things like locational pricing as well as pricing that can actually sometimes go negative. And essentially you have effects that depend not only on the cost of generation, but also on the physical constraints of the grid itself. And these do not disappear in a power market. They are very, very much prevalent. Now, this is really just skimming the surface in terms of the whole field of power markets. And a couple other points. In reality, we do run these markets at multiple time scales, right? So we run them once a day ahead, for example, because we have some maybe good idea about what loads are going to look like tomorrow, and we want to give generators time, the ones that take a while to start up, we want to give them time to get going so that they can be producing the power that we want at the time that they're required to. But there also are real-time, they're not quite real-time, they're sometimes 5 or 15 minutes ahead, but more real-time markets as well that say, okay, look, yesterday we were wrong in this way. We thought power would be X, but now being 5 minutes out, we actually know a lot more about what it's going to look like. Let's just go ahead and redo this whole process, taking a different set of bids to see who can provide power 5 minutes from now. And this is a very different process, right? Because the generators that can bid 5 minutes and offer to give this power 5 minutes from now might be very different from the ones that could bid to give power a day from now. For example, big coal plants and things like this typically take a lot more time to start up. Certainly nuclear takes a very long time to start up. And so they might not really be able to change their generation that much within the 5-minute time span, but they could plan a day ahead, versus other things like fast gas turbines can actually spin up very quickly, and so maybe they're going to want to bid in the real-time market because it's a little bit easier for them that way and they have an advantage that way. Now, there are other issues, though, in general. One of them is reserve power, and that is the fact that, look, even in the 5-minute case, there are actually even more hierarchies than this. There's reserve, and then there's things like frequency control, which we'll talk about a little bit when we talk about control. But the idea is that we have to have the grid operate smoothly at multiple resolutions, right? This kind of gives you a broad amount of power to allocate a day ahead, maybe 5 minutes ahead. But then there's all this kind of leftover stuff. Like you might have, I could turn on a light or not. I don't want to wait for another 5-minute market to work itself out before I get my light. So there is also what's called reserve power, which is essentially power that's the generators that are always ready to go. They're called spinning reserve because the generators are actually running. They're just not hooked up entirely. And so this is typically viewed in a little different way. This is viewed as kind of a grid service, and there are other markets for these services, not just the typical power markets that we're talking about here. So basically, you're just paid to have a certain amount of power ready to go at any amount of time, and you can figure that out ahead, how much you want to be paid and how much that's worth to you. I said also, reactive power is a bit different. Reactive power, because it has such high losses over long distances in transmission, it's almost always treated as a service instead and done locally. So there's things like voltage control and there's yes, governors, but then there's also it's compensator. Is that the right word? Anyway, there's various things like generators that can just generate reactive power that you can put at a substation level to essentially provide reactive power at that local level. And finally, another big issue here is who pays for transmission. So I've sort of left transmission out of all of this, right? We assumed it was kind of a fixed grid. Everything was assumed to be fixed, and power just flows as it will. But this is sort of a bit weird because if you buy some transmission lines, there's a sense in which you should be allowed to use that to put power over. But of course, physics don't care about who bought the line, right? Generators generate power. The power will flow over that line. So there is another entirely different set of markets for how you essentially hedge against the possibility that you will not be able to deliver your power even though you have it because lines are congested. And so this is not things we're going to talk about at all, but just this hopefully gives you sort of idea about what else is going on in this whole setting here. So with that, are there any questions about this? Okay, so with that concludes this bit on power markets. And now we are finally going to get to the little sort of mini extra unit on power electronics, which we didn't ever get to the first time. And the reason why we didn't get to it and was trying to get all this stuff working before. So I'm going to switch to that now. As I say, it is sort of a self-contained thing. We might want to finish it up a little bit next time, but I think I'll be able to get most of this done. So hopefully I'll have enough power cords to do all this. And I guess if not, we'll just see. So I'm going to switch computers here. So let me fire up this little guy. And actually, I can leave this computer on because I want to put my slides up still. Right. Okay. So we're going to talk about power electronics now, which are essentially things that happen when you do any kind of conversion from AC to DC, DC to DC, or DC to back to AC. These are sort of large power electronics here that we're talking about. And to motivate this, though, I'll sort of describe my experience going through this. I learned about AC circuits. I can't remember exactly when, but it was a while ago now. And you think you understand AC power. So, okay, DC power, that makes sense. DC is just direct current, always flows the same way. AC makes sense. There's real reactive power. These are all sine waves. Everything is nice because they're all just, you represent them as complex numbers, and it's all fine. And then I actually looked at what power actually looks like in, say, a home. I was doing all this monitoring for disaggregating data of energy data in homes. Knowing my bit of AC power and AC circuits, I assumed it was going to look like one thing, and it looked nothing like what I thought it would look like. Things do not look like sine waves at all when you look at the level of a home anymore, which is kind of bizarre. So I'm going to describe why that is. And will bring us to this work on power electronics. So we talked about transformers already. They're kind of the simplest kind of, it's not even power electronics. They're not called that because they're still all in the AC world, really, all in the linear world. What we're going to start talking about is rectifiers. Rectifiers are how you turn AC to DC power. But to do that, I'm going to give a little example of what power really looks like. So this might take a few seconds to load up here. And I'm going to describe what I have in a few little pieces. So let's see. OK, hopefully this actually works and I get a display here. I'll be very sad. It's even a really small computer, so if I don't have this, it'll be really hard to. There we go. OK, awesome. All right. So here's what I'm going to do. I'm going to plug in an A to D converter to this machine here. That's just a little, it's right here, a little box here that will take voltage signals, input into these guys, and convert them to floating point numbers so I can read it on the computer. So it's an oscilloscope, but it's just a digital one. And it's not even nearly as fast as most oscilloscopes you've probably played with. OK, so I'm going to do that. It's oh my! I can't believe I think I actually don't have a USB cable here. So I'm going to have to go run upstairs and find a USB cable, unless someone happens to have a USB cable. Does anyone? Oh no, I have one. Awesome. OK. I knew there was no way I'd have because there's so many parts to this thing. I knew there was no way I was going to have everything here. OK, so I'm going to plug this in. It's just a USB. It's actually a pretty nice A to D converter. It's like $1,000. I guess they aren't that. There's no reason for it to really be that much, but they're, other than all the software and all the kind of nice APIs that come along with it. OK, so what's going on here? All right, so I plugged in my A to D converter. Next, I'm going to plug in a voltage signal into that. And so what this thing is here, this is just essentially a reasonably high voltage transformers. We use it for oscilloscopes, essentially. Normally, you would have like 2 probes here that you would connect to whatever wires you wanted, but I just decided to plug onto it. So I'm going to plug this in somewhere. And what this will do is this will actually just step down the voltage. It's 120 volts, and those things can't handle that much. So it's a little less than that. Step it down to a little less than that. And then, can I set this somewhere? Yeah. And then read it digitally with this converter here. So let's see what this looks like. OK, is everything? I think everything's plugged in, but we'll see if this almost is certainly gonna, there's gonna be some issue here. It's not on right now, so it's not plugged in. That's the problem. OK. All right, and I have to get the resolution right here. So, OK. So here is the plot of the voltage. And what I'm doing is I'm reading the voltage. This is the actual voltage that you see in the line here. What I'm doing is I'm reading it, and I'm just finding the part where it crosses 0 and plotting just that part so it's aligned every time. I mean, if you just plotted it, the raw signals, it would look like a sine wave, but you couldn't really tell when it was. So I'm just reading a certain amount of data, looking for times where it crosses from negative to positive going that way, and then again happens here, and I'm plotting it in that range. That's why you see a little bit of jitter in this plot here. I guess I can't really, but if I turn it off, it'll disappear because there's no more. It should disappear. Oh no, actually, it just I think All right. I think I have it so it won't disappear, actually, even if the next one will disappear with what I'm doing. OK, so this just shows the voltage. This looks reasonable, right? This looks like what we expect. It's a little bit bumpy, actually. It's kind of weird. They're always like this. They're never actually that nice, the sine waves here. This is because big devices, especially big electronics, actually inject a little bit of noise in these signals, which actually corrupts the nice sine wave that you would normally see. And so there's little bumps here. But this is actually pretty good when you think about what we're about to see in a second when we talk about current. So talking about current now, what I'm going to do is, and I don't quite have enough plugs for this. I was hoping to use my plug over there, but I needed it for plugging this. Let's see if this all will reach. Boy, where do I? Huh. There's a plug over there, right? We have to get creative here. So, there's one over where?
The wall in that corner.
Yeah. I don't know if that'll reach. We'll give it a shot. I wasn't very, I put this in the wrong, whoops. I put this, let me actually show and keep in the video what I'm going to do right now. So what I'm going to do right now is measure, that's showing voltage. What I'm going to also next measure is current. So what I have here is a just power cable so I can plug loads into the end of the power cable. I got a really long one. Other stuff tangled up as well. This is a power cable where I cut it apart at one point and put a current transformer around one of those wires here. So what this is going to do is this is going to, for whatever's plugged into this power cord, it will monitor the current flowing through this wire. Right? And it's actually important to cut them open like this, because otherwise, if you put it over the entire wire, then you'll see both the current going one way and the other way, and those will cancel each other out. And so you'll get nothing. But if you open it up like this and put it around one end, then you'll see the actual current flowing through this wire. These current transformers, they're essentially just there's a little transformer. It is a magnet that goes around this thing. And an AC current, this is sort of a current that's oscillating back and forth through this, that creates a magnetic field here, which creates current or voltage differentials in this wire itself. So essentially current here will translate to a voltage difference here, and we're going to read this voltage difference using my A to D here. And hopefully we'll be able to find a place I can plug this in. Are there any on the back of that thing actually?
No.
No, okay. Boy, we'll see how this goes. I guess I can always move it just without having just move everything over this way. I just will have to be a little bit less in the frame. Okay, I think it might reach. There we go. Okay, so now what I'm going to show, of course I'm also low battery, so we'll see how long this lasts. So now what I'm going to show is the current. And it looks like nothing right now because I have nothing plugged into this, right? So it's showing something, but really this is just almost zero here, the current flowing through it. So let's look at a few different things. Let's look at, first of all, a light bulb. We turn this light bulb on, and it's not very well. That's actually weird. Why is it doing that? Oh, never had this happen before. What's happening here is that these are actually on different phases of voltage. Interesting. Okay, so I'm actually aligning to a different phase here. So the voltage phase coming out of this thing is not the same as out of that one, because this is plugged into something behind that, and it's not the same as that one. I've not ever seen that before when I do this. Anyway, shoot, this is supposed to look like a nice, let me see if I don't think I can reach that far, though, to get them both into the same one. Maybe I can if I sort of really move this around a lot. Let me do that just so I get a little bit better picture of what's going on. I guess I've already shown in the video what's happening. I can just move this all, I guess, over here. How do I want to do this? Okay. This is why it was hard to film this as an online video, by the way. This is the fun I was going, and it only works on a PC also, incidentally. Okay, what do I want to do here? Okay, I want to take this guy.
You're about to die.
Okay, well, I'll just plug that one in too then. Okay, well, I have an outlet open now, so that will be fine. Move this guy all over to here. Okay. You should not treat expensive hardware like this, I suppose, but okay. And now I need to go and, oops, I tore that out, of course. I need to go and plug the laptop into before it dies. All right, now what do I need to do left?
You use a smaller laptop in case you shock it.
I use a smaller laptop because actually these are laptops I used in the power monitoring hardware that I built to monitor power in homes, and it's the only Windows machine I have immediate access to that I can install whatever I want onto it. Nobody getting mad. This was actually quite a bit easier last year when I had a Windows PC I was using for this. So, okay, I think this should be working again. I think everything's plugged in. Let's see what happens when I plug in this light bulb now. Okay, that looks better. So now we're in the same phase in these two things. Actually, buildings like this, most homes will have two different phases. They actually have a voltage that goes into the house and a split transformer that makes two phases in the home that are 180 degrees out of phase. Most buildings have three-phase power. They just directly get the three-phase power from the grid, though. So it's kind of interesting, a little interesting fact that residential homes will have two phases that really just come from one phase, and buildings will have all the three phases, actually. Okay, so here's what a light bulb looks like, which is actually very much what you expect, right? This is a resistor. This is an incandescent bulb. It's a resistor. And there isn't really much else to say, right? It's a resistor. There's a pretty nice sinusoid for voltage, so the thing looks like a pretty nice, the current therefore looks like a pretty nice sinusoid as well. Let's plug in something, and I think I've dragged this on long enough, but let's plug in a few other things here. Let's take that LED bulb that I had that one time and plug that in. See what that looks like. So it's kind of similar, but there's some weirdness, right? It looks a little bit stranger. I mean, there's some noise. There's this weird little like plateau right there. What's going on with that? Move the mouse out of the way. So maybe it's just randomness that's causing it to look like that, but I don't think so. That would be really weird. Okay, let's look at one more now, and that will be, let's look at this computer. Hopefully I can transfer it without it dying on me. Quickly do that. Okay. Huh. So that's really strange, right? What's going on there? There's no way that could be a sine wave. So why on earth does it make that kind of pattern? So with that as our motivation, let's talk a little bit about power electronics, because this is why it looks like this. Power electronics are why it looks like that. The reason it looks like that is that the computer takes a DC signal as to power itself, not an AC signal. And to convert between an AC signal and a DC signal, all sorts of weird things happen. And we'll discuss that now, and we'll actually show exactly why we get a pattern like this. So, okay, let's talk about, I'll go back to the slides. Especially, does anyone else have anything they want to plug into this? It's kind of fun to see what things do. I would unplug one of these. I don't think I have anything else to plug in, but I would unplug one of these things, but I worry that I would destroy something would go wrong, right? Given the setup in this room. So this is actually pretty good. This is a pretty good this is very typical of what you'll see for a lot of electronics if you plug them in and look at their current signatures. So let's see what's happening. I'll just turn this all off and just shut it all down.
So we call those black boxes for PCs transformers, but they're not actually transformers, right? It's not AC to AC.
You're right. There is a transformer in there usually, but then there's other stuff as well. There's also an AC to DC converter in there. And yes, in this course we're calling transformers just the thing that goes from AC to AC.
Is that not typically usually
so it does two things. So transformers are they're AC to AC, but they basically change step down voltage or step up voltage, right? And so for those things, for a computer, you need to both change the voltage because it's not 120 volts DC. So there is a transformer involved as well. And I think sort of colloquially, you just refer to everything that changes voltage amounts as a transformer. It may or may not change to AC to DC. The thing that actually goes from AC to DC is called a rectifier, and we'll talk about that now. So really, these things are rectifiers and transformers. They usually have a transformer first, transformer to AC, and then, transformer to step down to like a low voltage AC current, and then a rectifier after that to make it DC. But we'll be specific. It's just transformer and rectifiers and kind of a mouthful for every time you want to talk about something you plug in, because they all have them, right? All electronics basically needs DC voltage. So okay, back to the slides here. Okay, so let's talk about a rectifier. And a rectifier is, oops, this is showing on the, oh, I need to change this now. Talking about rectifiers will bring us to the first nonlinear component that we've seen thus far, and this is called a diode. And all the other things we've seen, resistors, inductors, capacitors, they're all called linear circuit elements because you can, when you add them to a circuit, you can still manipulate everything with linear equations. And rectifiers are not like that. Rectifiers are fundamentally nonlinear. And the symbol for rectifier is this little thing here. And what intuitively this does, though you'll talk about a little bit more detail with the homework, you'll actually see what it does a little bit more specifically, is it essentially lets current flow in only one direction. So judging by the sort of intuitive from the arrow shape, current can flow this way, but it can't flow this way through the diode. Intuitively is how to think about it. So basically, if you have a positive voltage here, negative voltage here, then current will flow like this, sort of naturally. But if it's negative here and positive here, which happens in the AC source, of course, nothing will happen because current can't flow this way. Okay? And this simple diagram here is a very simple rectifier. And it seems, I'm saying this conversion from AC to DC. It doesn't quite seem like that, right? What it seems like is just sort of chops off half of what's going on. But that actually is to a crude approximation, that kind of is like that is essentially what a DC signal is like. So maybe I'll just draw that. So what this circuit will do, and I'll actually work it out in Quux in a second, because we're going to do a different type of analysis in Quux now, which is actually transient analysis. We actually see the actual current and voltage waveforms over time. But you might imagine, right, here's the full AC signal. This will let, this is the voltage here. That's 0. So this will let current flow only when the voltage is positive here and negative here. So essentially, suppose that's just a resistor, and ignore this capacitor for a second. Just ignore that. What this will do is, well, here the voltage is positive. It's positive on the top. So current looks something like that, say. Here it's just 0, because the current can't flow the other way. And so here's positive again. And if you sort of blur your eyes, right, you can imagine this is looking more like a DC signal, because it's only positive now. And if you take an average, something like that, this could be somewhat positive. It turns out what we'll actually do is we'll put a capacitor here. And this capacitor builds up charge, right? So if current's flowing this way, this capacitor will build up charge. When current stops, the capacitor will then supply the current. And so essentially, you will essentially smooth this out, and you'll get something like the average of this thing. It's not quite that smooth, but you get something like the average of that when you add the capacitor there. The capacitor is big enough. So that's basically how a AC to DC works. I mean, you take a simple one. It's called a half-wave rectifier because it looks at only half the wave here. But that's how it works. So let's take a look at what this looks like in our circuit simulation. I won't build all of these because it's kind of a repetitive process that you went through on the homework, and we don't have to do it too many times. But let's place everything here. Actually, whatever. I'll just do it. Well, no, I'm going to mirror my desktop because it's kind of a pain to look up there. Okay, everyone can kind of read that. It's not great, I know, but you've worked with it before, so hopefully it'll be somewhat intuitive. Make it a little bigger. Oops. Maybe zoom in. Okay, so let's add an AC source. Let's just set up this circuit essentially. Here's our AC source. Let's just make it 10 volts just to have something that's a little bit more than 1. Put our resistor over here. Say it's just 1 ohm. And let's put our diode, which will be a nonlinear component. Put our diode here. And let's just wire it all up. Have that wonderful cursor, which is not near the actual components. Okay. And let's just actually add let's just leave it as it is right now. Let's just add a current probe, see what this does. Okay, so here's our simple circuit. We're doing something a little different this time where instead of a AC or DC simulation simulates steady state AC or DC current and voltage. That's not what we want here. There is no steady state really anymore. These things, by definition, I mean, you have to look at the actual evolution of the waveforms over time, or they don't make any sense. So what we do instead is drop what's a transient simulation block here, and that essentially says how long to, when do you start? Starting everything's uncharged, or at least by default it's uncharged. Let's make it go to I should change the frequency of that too. Let's make it go to 0.1 seconds. Okay, here I have to change the frequency. 60 hertz. Okay. And I think that's all we need to do to run it. Am I missing anything?
The transient simulation thing changes what data you can get out of it.
So what the transient will do is AC and DC simulate what is the steady state voltage and current you get from this thing when you let it sort of settle to whatever it is. And for AC, that's actually easy because every single sine wave is the same. Here, they're actually different. And so what it does is it actually gives you a plot like this, where for every time point at some fine resolution, and actually I need to step up. One thing I have to do is, this is essentially the number of simulation steps you get. So let's say it's like 1,000. It might be too many. We'll see if that actually works or not. I think, this is rectifier. Oops, I needed a ground. Okay. All right, so I simulated it. And now instead of like a single just table plot, which is what you guys did before, we're actually going to show a Cartesian plot of what's actually happening over this time. So let's show a plot of the, let's actually just plot the voltage first to make sure, oops. Oh, I plotted it at the wrong spot. That's kind of the punchline there. That's actually what it looks like. Boy, I delete. Can we show the voltage actually in V1? Oh no, actually that's just showing current. There's simpler ways to do this, but let me just be explicit here and put a voltage probe. So let me put a voltage probe in, apologies for the ugly wires there. Okay. And let me now plot the voltage from that guy. And that should just look like a sine wave because, of course, it's just, we're just, oops, voltage. Okay. Okay, that's just our sine wave there because I'm just plotting the voltage of the actual source itself. Maybe a little bit bigger. And now let's plot the current that flows through this on the other axis. So now let's plot, or on the same axis rather, what the current looks like. Yeah. I want the, boy, and current. And what, I don't know what that is, but I want to delete that. Okay, apply. All right, there we go. So current now, as you imagine, it just follows voltage, but it isn't, you know, when that's negative, it doesn't do anything. You might be wondering why this is actually a little bit lower. It should be the exact same thing, right? Because it's 1 ohm resistor. Quux is actually reasonable at modeling diodes, and there is some resistance to a diode. This diode is not actually an ideal diode. That's that. Sort of funny because sometimes what people call ideal diodes actually do have some loss still too, but because the real ones are even worse than that. But it's not a lossless thing, that diode. There is some resistance. There is some loss to it.
And it's not a constant offset in real with a real diode.
Sorry, what's the what a constant offset?
The ideal diode is just the same. It acts like a negative 0.6 voltage source. That a real diode doesn't have like a constant offset.
So a real diode. I mean, so there are two things here. So ideal, I would mean like a lossless diode that actually just lets current flow in one direction, and that would give nothing here. Yes, ideal real diodes will have a voltage drop, but the thing is, what people call an ideal diode is something that's governed by Shockley's equation, which has a voltage drop to it. So an ideal diode, when people talk about what an ideal diode means, there actually usually is a voltage drop across it. And real diodes are even worse than that. I mean, they have like back current can flow, the current can flow the other way. There's breakdown voltage, all those kind of other things that have different effects, and isn't, of course, perfectly modeled by this equation either. All that, don't worry about it yet, but you'll actually work through that on the first problem of the next homework, so it will all make sense, hopefully. But yes, there is a voltage drop across that diode, essentially.
It's not linear.
It's not linear, no. It's definitely, I mean, it's the voltage drop is, yeah. It's very nonlinear function of the current, yeah. Okay, so here's what it looks like. And now let's kind of smooth that out a little bit. Let's first just get rid of the voltage, though, and just look at the, delete that one. Okay, let's just look at the current now. And now let's add a capacitor. And as I said, what the capacitor is going to do is it's going to kind of build up charge when current is flowing here. And then when it's not flowing, so when we're down here, it'll let current sort of supply voltage to the thing itself. So it'll essentially take this and it'll average it all together. And I think like 1 millifarad should be plenty for that. I could be wrong about that, but let's see. Okay. All right, let's simulate that and see what it looks like. Oh, I'm very wrong. Well, I think I just have my constants a little off here, but that's actually not a very realistic system. But wait, I did something's not connected here. This is strange. Should not need that much, but let's just make a pretend system. Okay, what's going on here? Do you want to see what I'm doing wrong here? I think I don't have some element or something, and I'm worried that it's doing weird stuff because this is all over here. But basically, this is building up a lot of charge. I think I have it connected somehow not correctly, or it's actually modeling these things more miraculously. You know what? Let me just open up the thing that I know works. See what I'm doing wrong. Of course, I think actually maybe this is just the totally wrong resistance there for that to actually be reasonable for this diode. But Yeah, actually, I think that's what it is. Is that this diode and then that resistance doesn't really make sense together. 50 ohm. And first of all, let's just make it small so nothing happens here. Wait. Oh, I didn't change it there. Boy, what's going on here? So this is the wonders of this program that are, it's now,
Press escape and then go back.
yeah.
By the way, how do you do that trick where you just click to turn it?
The trick where you click to turn it?
Yeah.
Um,
Like controls?
yeah, it's the right click, just rotates the things.
Okay.
I forget what, let's see. I feel like I did something incorrect in the setup here, but I'm not quite seeing what this is.
What is that value by the diode?
Right, so these are all parameters for that Shockley equation, which essentially govern how the diode works. But what's really strange here is that it's not working. So yeah, this is just bizarre. Let me try this one. Or did I have something wrong with this guy? I don't know. That's actually okay. I feel like I must have just set up this equation somehow incorrectly. Huh. Okay, let me just try it in this one instead. This is the same thing. I'll just try setting it up in the same way. Zero stop. Okay. Oh, I know what I'm doing wrong. Okay, so I'm actually showing you exactly what you saw on the thing. What I meant to be showing is the current, obviously, is the current through here, not the current through there. What I'm showing you now is actually exactly what you saw in the thing, just one half of it. Okay, now it makes sense. So let me just fix this. Let me show you what I want to show you, which is the probe here. Boy, this is getting even more fun as I go, the graphics. Look at that. Now it's like placing this somewhere else. Okay. Now let's get rid of these guys too.
So what we see now is what we saw through the wire when you connected.
Exactly. Which I was going to show you second, but that's actually only going to do it in the case of the full wave rectifier because it's a little bit less intuitive here. Okay, so now let's do this instead. Let's simulate this one. And what you see here, of course, this is exactly what I was looking for. Okay, so here what's happening is what you expect. Oops, yeah, whatever, let me just change it back. Okay, so the current starts following the sine wave at first. But essentially what happens then is when this is first happening, you build up charge here. And so then when it goes the other way, and even actually at first, before it even falls off, when it starts falling off, the voltage is lower than the voltage across this capacitor here. And so the capacitor will start to supply the current itself. Supply the voltage, rather, that causes that current. So you'll get a current. And the bigger capacitance here, potentially the flatter this will look because you'll store more and more current. So if I make this 10 millifarads, then that would smooth it out a little bit more. Okay, so that's sort of what we expect, right? It's sort of we took this sine wave, and it would look like a sine wave if I didn't have any capacitor there, as we saw before. But because we add that capacitor there, essentially it builds up charge. Charge drops this whole time. So this whole time is dropping voltage because the capacitor itself is acting as a voltage source. And then when you come to this little lip here again, it will charge it back up. and that will repeat that process. So this is a AC-DC converter, right? We've taken AC source here, gone through a bunch of stuff, and we have a DC signal in the end. And what you saw on the other graph is what happens at the current, in terms of the current flowing through the source wire. So in this guy, this guy here was my power source for my computer. Everything on this end, basically it plugs in here, right? So that's where it plugs in, and everything behind it is where it's supplying the DC voltage and current, but we don't see that. What we see are the wires leading into that, and we were looking at the current going into that. So before and so what you saw there is also intuitive. And let me actually, I can just put that in the same plot here. Okay. Okay, so it's actually hard to see because they're on very different scales here. But essentially, what's happening is that at the time you're building up, first there's going to be a very high current through here because you're building up voltage. And essentially, you're both charging the capacitor and powering that thing. Then at subsequent times, you're only going to draw actual current when the voltage here is bigger than the voltage here. Otherwise, you just get the voltage from the current from the capacitor, right? You won't be actually using this current at all. And so what ends up happening is that it's only for a few little blips like this that you're actually drawing current from the source. That's providing all the current, all the power of the system is coming from the few little blips in time where you sort of see now my voltage here, drop here, is higher than the voltage drop here. That will cause a lot of current to come in to charge that capacitor so that it can keep supplying the voltage itself. Does that make sense? What's happening there?
How does it demand current? Like, what I mean is, like, how does that voltage source not just always a 60 Hertz sine wave? Right.
So for a voltage source to actually provide, for it to draw any current, there needs to be a load on the other side. So this is showing current, not voltage. The voltage source is constant, right? So the voltage itself is constant. This is showing the current is being drawn from that. And the only way in which you draw current is if this voltage drop is bigger than this one here. Otherwise, otherwise it wouldn't, because current can't flow the other way, right? So it only can flow this way, and it will only happen if this voltage drop is less than that one. So essentially, the first time around, you use a lot of current to charge that capacitor up to the point where you do actually have this thing being always bigger than that one over there. So first, the capacitor will essentially draw a lot of that current. After that, you will only see, let me just show the other one again.
So that's really cool. That's why the constant on the grid is that it has to be at 60 Hertz for voltage supply, but then the load will change the current draw, and thus change the actual power that you need.
So the load will draw whatever current needs as if it was coming from a DC source, right? It's just that the capacitor, so what's happening here is this is sort of the look of the current, right? So it's just this little blip right here that you're actually going to be drawing current from the voltage source, because that's when you actually need to recharge that capacitor. And then after that, in this range, the capacitor is just providing the voltage itself, right? Let me, in the quick time we have, and I had this one pre-made, so it won't take as long. Let me just show you that this is sort of nice and kind of makes sense, but it also seems to be kind of wasteful, right? Because we're only using, in some ways, kind of half the available current here, or half the available voltage. We're just ignoring the other half of it, and that seems like it's somehow unbalanced. So what people do actually is use, in practice, they'll use what's called a full wave rectifier, and this is, you need 4 diodes now rather than just 1, but this is something that actually lets you get current that looks like this. So let me just go through this. When this side is bigger than that side, then current will flow, won't go that way, it'll go this way and flow through it this way. So if this is positive, this is negative, it'll go this way. If this is positive and this is negative, it will go this way and then come back and go like that. So whether this is positive here, negative here, or positive here, negative here, current will flow the same way through this element over here. And so the current will look like this. It'll look like these two bumps here. And this is kind of nicer because now we're kind of using all the available current and voltage in some sense. And what it looks like, and the diagram is exactly what you saw in the little plot there. So let's open that up. Oh, and I took everything out. Dang it. I don't know why I did that. Let me add the everything fast as I can. Oops. Okay. Maybe 0.2. No, that wasn't. Okay. Let me add a capacitor here. I have everything that I need here. Should be like I should maybe just make it 1. That's smoothing a little bit too much otherwise.
You're not probing.
Yeah, I know. So let me first add a probe to this side of things. And then we'll add one to this side of things. No, that's not what I wanted either. I didn't want there. I wanted this side of things. Okay. And let me add, first simulate. Okay. And now let's look at what this thing looks like. Look what the current through the element looks like. It looks reasonable, right? So it's sort of DC. Let me make that a little bit bigger, actually. And you know what? This time, actually, let me change the transient simulation this way. So that looks a little better. Let me change this so that we don't start at 0, so we don't look at the time when it builds up charge. Let's just look at the time when it's settled to its steady state. I mean, steady state in a different sense than AC steady state. But let's just look at that. Okay. So that's what the current through the element itself looks like. So this is a DC signal. I mean, it's actually a little nicer because we get both of these things, and so you have to smooth it a little bit less, and it looks a little smoother for the same amount of total capacitance and everything. But now let's look at what the signal looks like on the other side, which is this one. So this is exactly what we saw from the computer there. So I mean, to a first order approximation at least. So this is exactly what we'd expect, right? Because basically what's happening is that the only time when you are actually drawing current from that source there is when this voltage is less than whatever the total magnitude of that voltage is. And if this one is one way, it's sort of, if it's positive here bigger, then it'll draw this way. If it's positive on top bigger, it'll draw this way. And so this is why, this is exactly what's going on inside that little thing. There's a transformer first probably that steps down to a reasonable voltage. Then there's a rectifier. Then there's probably actually a voltage regulator after that, which is actually just like a lossy component. This is why these things get so hot. There's losses in other things as well too. But that's what is happening. And that's why the signal in a home looks nothing like an actual sine wave. Because I mean, there's so many electronics in the home now that you see a ton of these things. If you were to plug in and monitor the current, say, on the mains in the house, you'll see something that looks much more like, not looks like this, but it'll have these obvious peaks at the peaks of the sine wave and the troughs of the sine wave. So we'll cover the last couple elements on the nonlinear circuits as well next time, just to finish it up. But this is sort of getting across some of the main ideas there, both seeing it and then seeing the theory of why it works out that way. So, all right, see you guys next time.
Ah!